Welcome friends to this 14th lecture of multivariable calculus on extreme values. Myself Dr. Sanjay Madhukar Chinchole. In the previous lecture, we have learned the maxima and minima of functions of two variables, to study the critical points and saddle points of functions of two variables, to study the second derivative test to determine the critical points and saddle points. In this lecture, we are going to solve the problems on second derivative test and study extension of closed interval method. Example, suppose 1 is a critical point of a function f with continuous second derivative such that f(x)(x) of 1 is equal to 4, f(xy) at 1 is equal to 1 and f(y)(y) at 1 is equal to 2. What can you say about f? Here we want to use the second derivative test. To apply the second derivative test, we want to find first of all the discriminant d at the point 1 that is equal to f(x)(x) at 1 into f(y)(y) at 1 minus f(xy) at 1 bracket square, which is equal to 4 into 4 is f(x)(x) at 1, 2 is f(y)(y) at 1 minus 1 square, that is f(xy) 1 square. It is equal to 4 into 2 is 8 minus 1 square is 1. 8 minus 1 is equal to 7, which is greater than 0. That means the value of discriminant at 1 becomes greater than 0. So 1 is either minimum point or maximum point, and we can decide its minima or maxima on the value of f(x)(x) at 1. If it is positive, the point 1 becomes a minimum point, and if it is negative, the point 1 becomes a maximum point. See, as f(x)(x) at 1 is equal to 4, it is positive, so we can say that by second derivative test, f has local minimum f at 1. Next example, suppose 1 is a critical point of a function f with continuous second derivatives such that f(x)(x) at 1 is equal to 4, f(xy) at 1 is equal to 3, f(y)(y) at 1 is equal to 2. What can you say about f? This is same as that of the previous problem. So again we want to use the second derivative test, and we have to find a d at 1 by using the same formula, f(x)(x) at 1 into f(y)(y) at 1 minus f(xy) at 1 bracket square. Here the values are changed, so this value becomes 4 into 2 minus 3 square. It is equal to 8 minus 9 is equal to minus 1, which is negative. And we know that when this discriminant becomes negative, the corresponding point is a saddle point. So by second derivative test, 1 is a saddle point of f. Next example, find the local maximum and minimum values and saddle points of the function f of xy is equal to x square plus xy plus y square plus y. To find local maximum and minimum values, we want to find its extreme points, and for that, first of all, we have to find the critical points of function f of xy. For that, we want to find the first order partial derivatives of f of xy, as fxy means partial derivative of f of xy with respect to x. It is equal to derivative of x square is 2x plus derivative of xy is 1 into y, that is y, and the derivative of y square plus y, which is independent of x, so its derivative becomes 0, and indirectly we can say that fx at xy is equal to 2x plus y. Similarly, its partial derivative with respect to y becomes fy xy is equal to the derivative of x square, as it is independent of y, becomes 0, plus x into derivative of y is 1, that is x, plus derivative of y square is 2y, plus derivative of y is 1. So the partial derivative of f with respect to y becomes fy at xy is equal to x plus 2y plus 1 is equal x plus 2y plus 1. To find the critical points of f of xy, we have to equate fx at xy and fy at xy with 0, and we will get 2x plus y is equal to 0 and x plus 2y plus 1 is equal to 0. 2x plus y is equal to 0 gives us y is equal to minus 2x, and we can substitute this y is equal to minus 2x in this another relation. We will get x plus 2 into bracket minus 2x is equal to minus 1. So it will be x minus 4x is equal to minus 1, means minus 3x is equal to minus 1. So it will be 3x is equal to 1 and x is equal to 1 upon 3. Now we can substitute x is equal to 1 upon 3 in this first relation, y is equal to minus 2x. So we'll get y is equal to minus 2 upon 3 and x is equal to 1 upon 3. So 1 upon 3 comma minus 2 upon 3 is the only ordered pair of critical point of function f of xy. Now we want to decide whether this critical point is saddle point or local maxima or minima. For that we want to use again second derivative test. For that we have to find fxx at xy, fyy at xy and fxy at xy, and then for the point 1 upon 3 minus 2 upon 3. As from the first order partial derivatives, fx at xy and fy at xy, that are 2x plus y and x plus 2y plus 1, we can get fxx at xy and fyy at xy and fxy at xy as fxx at xy is equal to 2, fxy at xy is equal to 1, fyy at xy is equal to 2. This is the partial derivative of fx with respect to x, this is the partial derivative of fx with respect to y, and this is the partial derivative of fy with respect to y. Now as all these values becomes constant for any x values of x and y, we'll get these values as it is. So fxx at 1 by 3 minus 2 by 3 is equal to 2, fxy at 1 by 3 minus 2 by 3 is equal to 1, and fyy at 1 by 3 minus 2 by 3 is equal to 2. And hence we have discriminant d at 1 by 3 minus 2 by 3 is equal to fxx at 1 by 3 minus 2 by 3 into fyy at 1 by 3 minus 2 by 3 minus fxy at 1 by 3 minus 2 by 3 square is equal to 2 into 2 minus 1 square. It is equal to 4 minus 1 is equal to 3, which is greater than 0. That means this point 1 upon 3 minus 2 upon 3 is not a saddle point of function. Means it is either local maxima or local minima, and it will be decided from the value of fxx at xy. If it is positive, the point is local minimum, and if it is negative, the point is local maximum. Obviously this fxx at xy is equal to 2 means fxx at 1 by 3 minus 2 by 3 is equal to 2 is positive. So 1 by 3 minus 2 by 3 is local minima of function f, and the minimum value can be obtained by substituting s is equal to 1 by 3 and y is equal to minus 2 by 3 in the formula of function. So it will be f at 1 by 3 minus 2 by 3 is equal to 1 by 3 square plus 1 by 3 into minus 2 by 3 plus minus 2 by 3 square plus minus 2 by 3. It is equal to 1 by 9 minus 2 by 9 plus 4 by 9 minus 2 by 3. So this 1 by 9 minus 2 by 9 plus 4 by 9, it will be 3 by 9. That means 1 by 3 minus this 2 by 3 as it is, and at last we will get minus 1 by 3 as the local minimum of f. Next example, find the local maximum and minimum values and saddle points of the function f of xy is equal to xy plus 1 upon x plus 1 upon y. Similar as the previous problem, we first of all find the partial derivatives of fxy with respect to x and y, that are fx at xy is equal to x into fx at xy is equal to y into derivative of x is 1, that is 1 into y, that is y. Derivative of 1 upon x is minus 1 upon x square, and 1 upon y is independent of x, so its derivative will be 0. Similarly, derivative of fxy with respect to y will be fy at xy is equal to x as it is, derivative of y is 1, x into 1 is x, 1 upon x is independent of y, so its derivative becomes 0, and the derivative of 1 upon y will be minus 1 upon y square. Now to find the critical points, we have to equate these two values with 0, and we'll get y minus 1 upon x square is equal to 0 and x minus y 1 upon y square is equal to 0. So y is equal to 1 upon x square and x is equal to 1 upon y square. As y is equal to 1 upon x square, this x minus 1 upon y square is equal to 0 can be written as x minus 1 upon x square bracket square is equal to 0. Indirectly it will be x minus 1 upon x raised to 4 is equal to 0. So it will be x minus x raised to 4 is equal to 0. By factorizing this, we will get y is equal to 1 upon x square, and either x is equal to 0 or 1 minus x cube is equal to 0. This 1 minus x cube is equal to 0 gives us x cube is equal to 1. That means either x is equal to 0 or x cube is equal to 1. When x is equal to 0, y cannot be defined. So x is equal to 0 is not a valid value for x. So we have to just consider x cube is equal to 1 and y is equal to 1 upon x square. Okay, and this x cube is equal to 1 valued only for the real value of x, that is equal to 1. So we will get x is equal to 1 and y is equal to 1 upon x square. That means y is equal to 1 upon 1 square, which is again equals to 1. Therefore 1 is the only critical point of f of xy. Now we have to decide whether it is saddle point or local minimum or maximum. For that again we want to use second derivative test. For that we want fxx at xy, fxy at xy, and fyy at xy. From the first order partial derivatives, fxy is equal to fx at xy, that is y minus 1 upon x square. When we differentiate it with respect to x, again we will get fxx at xy is equal to 2 upon x cube, and that fx at xy is equal to y minus 1 upon x square. When we differentiate it with respect to y, we will get fxy at xy is equal to 1, and similarly fyy at xy becomes 2 upon y cube. Now we want to find these values at the point 1 1. At the point 1 1 we will get fxx at 1 1 is equal to 2 upon 1 cube, that is 2. fyy at 1 1 is equal to 2, and fxy at 1 1 is equal to 1. And from that we will get the discriminant d at 1 1 is equal to fxx at 1 1 into fyy at 1 1 minus fxy at 1 1 bracket square is equal to 2 into 2 minus 1 square. It will be 4 minus 1 is equal to 3 greater than 0. Again from this we can say that the point 1 1 is not a saddle point, and its local minima or maxima will be decided from the value fxx at 1 1. As it is 2 greater than 0, we can say that 1 1 is the local minimum function, and its minimum value can be obtained by f at the point 1 1 is equal to 1 into 1 plus 1 upon 1 plus 1 upon 1 by substituting x is equal to 1 and y is equal to 1 in the formula f of xy, and indirectly we will get the f of 1 1 is equal to 3 as the minimum value of f, local minimum of f of xy. Extreme value theorem for functions of two variables. If f is continuous on a closed and bounded set D in R2, then f attains an absolute maximum value fx1 y1 and an absolute minimum value fx2 y2 at some points x1 y1 and x2 y2 in D. This extreme value theorem states that if f is continuous on closed and bounded set D in R2, then f must attain an absolute maximum value at some point and absolute minimum value at some point in D. Extension of closed interval method. To find the absolute maximum and minimum values of a continuous function f on a closed and bounded set D, we have to follow the following step. First step, find the values of f at the critical points of f in D. Find the extreme values of f on the boundary of D. The largest of the values from step 1 and step 2 is the absolute maximum value. The smallest of these values is the absolute minimum value. So first of all we have to find the critical points of f, then its value in D. Again we want to find the extreme values of f on the boundary of D, and then from both the types of values we have to select the maximum as absolute maximum value of f in D and minimum value as the absolute minimum value of f in D. Example, find the absolute maximum and minimum values of function f of xy is equal to x square minus 2xy plus 2y on the rectangle D is equal to set of all xy where 0 less equal x less equal 3 and 0 less equal y less equal 2. So D is the rectangle where the side of rectangle has the x coordinate lies between 0 and 3 and y coordinate lies between 0 and 2. First of all, we have to differentiate f of xy with respect to x and y partially to find the critical points, that is fx at xy is equal to derivative of x square is 2x minus derivative of 2xy with respect to x, that is 2y into 1, that is 2y, and the derivative of 2y is 0 with respect to x. So fx at xy becomes 2x minus 2y. Similarly, fy at xy is equal to derivative of x square with respect to y becomes 0, minus 2x is constant, derivative of y is 1, so it will be minus 2x, plus 2 into derivative of y is 1, so it will be 2. Fy at xy is equal to minus 2x plus 2. To find the critical points, we have to equate them with 0 and we will get 2x minus 2y is equal to 0, that is 2x is equal to 2y or x is equal to y, and minus 2x plus 1 is equal to 0, that is 2x is equal to 2 or x is equal to 1. When x is equal to 1, we will get y is also equal to 1. So 1 1 is the only critical point of f, and at the point 1 1, the value of function is 1 square minus 2 times 1 into 1 plus 2 times 1, that will be 1 minus 2 plus 2 is equal to 1. Now we want to find the values of function f on the boundary of rectangle D. We looked at the values of f on the boundary of D, which consist of 4 line segments. As it is a rectangle, it has a 4 line segments. We will denote them by L1, L2, L3, L4 as shown in figure. See, this is a rectangle where the values of x lies between 0 and 3 and the values of y lies between 0 and 2. Okay. Along the line L1, we can observe that the x coordinate is 0, so its equation is x is equal to 0, and the value of y is from 0 to 2, so we can say that x is equal to 0 on the line L1, and when we substitute x is equal to 0 in the function, we will get f at 0y is equal to only 2y. Okay, where the value of y lies between 0 and 2. So its minimum value is at the point y is equal to 0, that is 0, and maximum value is at the point y is equal to 2, that is 2 into 2, that equals to 4. Okay. Similarly, on the line L2, we have y is equal to constant, that is y is equal to 2, while the value of x is from 0 to 3. So the function becomes fx2 when we substitute y is equal to 2. Fx2 is equal to x square minus 2x into 2 plus 2 into 2, that will be x square minus 4x plus 4, which is equal to x minus 2 bracket square. It is the expansion of x minus 2 bracket square where the value of x lies between 0 and 3. So its minimum value will be at x is equal to 2, that will be 0, and the maximum value will be at x is equal to 0, that is 4. This is a function of x with minimum value f at 2 is equal to 2 minus 2 bracket square is equal to 0, and the maximum value at f at 0 2, it will be 0. F at 0 2 is equal to 0 minus 2 bracket square, that means minus 2 square, it will be 4. So instead of f32, you have to read it as f of 0 2, 0 minus 2 bracket square, it will be minus 2 bracket square is equal to 4. Along the line L3, we have x is equal to constant, that is 3, and the value of y lies between 0 and 2. So the function becomes f3y is equal to 3 square minus 2 times 3 times y plus 2y, that will be 9 minus 6y plus 2y, that is 9 minus 4y, where the value of y lies between 0 and 2. So its minimum value is y is equal to at y is equal to 2, and the maximum value is at y is equal to 0. So at y is equal to 2, it will be 9 minus yet is equal to 1, and maximum value is at the y is equal to 0, it will be 9 minus 4 times 0, that is 9 minus 0 is equal to 9. Along the line L4, we have y is equal to 0 and the value of x is from 0 to 3. So the function becomes fx at fx comma 0, it will be x square minus 0 plus 0, so it will be just x square, where the value of x is from 0 to 3. So its minimum value is at x is equal to 0 and maximum value is at x is equal to 3. So its minimum value is 0 and maximum value is 9. Overall, at all the points on the boundaries, we can compare the values. The value of function at critical point becomes f11 at is equal to 1, while the values on the boundary points will get the maximum values at 30 is equal to 9, and the minimum values at f00 is equal to f22 is equal to 0. So in all, we can say that the absolute maximum value of function is 9 at the point 30, and the absolute minimum value of function is at the point 00 and 22, that is equal to 0. Thank you. If you have any question, you can find me at mrsanjaymaths@redifmail.com or mrsanjaymaths@gmail.com.